Welcome to this lecture in linear algebra. Today we're going to talk about the direct sum of vectors of two vector subspaces, and it is closely linked to the fact that to the definition of subspaces and the vector spaces. But before that, we actually have to define what the sum of two subsets actually means. Okay, so definition. And I believe this is the third one. Let's see, yeah. Definition 3. So let S1 and S2 be subspaces of a subset of a set S. And they have to be non-empty. Okay? So they cannot be the empty set. Then we define the sum of these two sets. Right, this is defined to be the set of vectors x, of elements x plus y, where x belongs to S1 and y belongs to S2. Okay, so it is the set of all the sums of the vector of the elements in S1 and the elements of S2. Okay, we can now use this definition, right? Because definition 4 is where we define the direct sum of two vector subspaces. Okay, so let W1 and W2 be subspaces of a vector space V over the field F. Then for y1 direct sum with y2 to be equal to V, we need the following conditions to be met. Okay, and this is equivalent to this set of conditions. Okay, so the first condition is that y1 intersection y2 contains only the zero vector, right? Obviously, it can't be empty because all vector subspaces need to contain the zero vector. That's the third condition for a subset to be a subspace. So the zero vector has to be in the intersection, but nothing else. And then the second condition is that y1 plus y2 is equal to V. And here is where definition 3 comes into play. And obviously, W1 and W2 have to be subspaces of V. Okay, so now we can use this to solve an exercise. So let C from 0 to 1 be the family of continuous real-valued functions. So the family of continuous real-valued functions. And define f1 t to be equal to t and f2t to be equal to t to the fourth for t belonging to 0, 1. And let M, okay, so we define M to be the set of all functions alpha f1 plus beta f2, and we'll define what this is in mathematical terms. It's a linear combination, spoiler alert. Okay, so for every alpha and beta belonging to the field we're working on is R, right? The field of real numbers. Okay, similarly, we let n be the family of functions G belonging to C which satisfy this rule, right? So the integral from 0 to 1 of gt dt, of t times gt dt, has to be equal to 0, and also the integral from 0 to 1 of t to the 4th times gt dt must also be equal to 0. Okay, so n is the set of all the functions gt which satisfy these two conditions. And we want to see whether or not m direct sum n is equal to c. Okay, so let's see. How can we prove this? Well, first of all, the very first thing we have to do is show that m and n are subspaces of C. Okay, so very first point is to show that m and n are subspaces of C. Okay, so how can we do that? We have to verify the three conditions. So first of all, does the 0 function belong to m? Clearly, if we take alpha and beta to both be equal to 0, then yes, 0 does belong to m, and that is good. So this is actually the third condition. The third condition is met. We also have to show that there is closure in addition. So if we take for every m1 and m2 belonging to m, then the addition, right, m1 plus m2 has to belong to m. Is this true? Let's see. So m1 plus m2, well, we can actually write this knowing the fact that they both have to be the sum of alpha f1 and beta f2 for some alpha and beta. So we can write this as alpha 1 f1 plus beta 1 f2 plus alpha 2 f2 f1 plus beta 2 f2, right? This is equal to m1 and this is equal to m2. Okay, how we can rewrite this as alpha 1 plus alpha 2 f1 plus beta 1 plus beta 2 f2. And clearly, if we let alpha be equal to this and beta be equal to this, then this function right here belongs to m, because it is in the form real number times f1 plus real number times f2. Okay, so we know it is closed under addition. Let's just show that this is also closed under scalar multiplication. So for every alpha, no, let's not use alpha, let's use gamma belonging to R, right? Gamma m1, right, where m1 belongs to m, is equal to gamma times alpha f1 plus beta f2. We can distribute this and say that this is equal to alpha gamma f1 plus beta gamma f2. Beta gamma f2, and clearly this is again in the form real number times f1 plus real number times f2. So this also belongs to m. Great, so we showed that m is a subspace, right? It is closed under scalar multiplication, addition, and 0 belongs to it. Let's do the same with n. Okay, so how do we do this? Again, does 0 belong to n? Well, if we recall the definition, right, n is any function such that the integral from 0 to 1 of gt times t dt is equal to 0. Is this true? Well, if we substitute 0 here, we get the integral from 0 to 1 of t times 0 dt, and this is equal to 0. Okay, so we saw that the integral from 0 to 1 of t times gt is indeed equal to 0 if we let 0 belong to n. We also have to do the same with t to the fourth, right? And obviously it's going to be the same thing, right? Because we get t to the fourth times 0, and this is just 0. Okay, so 0 does belong to n. Because of these two integrals, let's now show that it is closed under addition. So for every g1 and g2 belonging to n, right, does g1 plus g2 belong to n? Question mark. Let's see if it satisfies these two integral conditions. So if we take the integral from 0 to 1 of t times g1 plus g2 g1 plus g2 t dt, well, we can distribute this t over, so we get the integral from 0 to 1 of t, or actually let's rewrite it a second. Okay, so we can distribute the t and then split off the two integrals. And now recall, g1 belongs to n, which means that the integral from 0 to 1 of t times g1t must be equal to 0. Okay, so this integral right here must be equal to 0 because g1 belongs to n. Same goes here, and so this is equal to 0. Okay, obviously the same works with t to the fourth, I'll just leave it up to you. So clearly g1 plus g2 does belong to n. Let's do the same for scalar multiplication. So for every alpha belonging to r and g1 belonging to n, right, is alpha g1 a member of n as well? Well, let's see again. Let's use the integral from 0 to 1 of t times alpha g1 t dt. Okay, using the properties of real valued functions, this is equal to t times alpha g1 t dt. And again, using the properties of integrals, we bring the constant alpha out. And because g1 belongs to n, this integral right here is equal to 0, and so this integral is equal to 0. And the same goes for t to the fourth, you can just substitute it here, and you get 0. So again, alpha g1 does indeed belong to n, and so from these two we see, from these three conditions, we see that n is a vector subspace of C. And also m. Okay, so we've got one part of the proof down. We've shown that these are subspaces. Next step is showing that we have to show that m intersection n only includes the zero function. Okay, so suppose there's a function h which belongs to both, okay, actually let's call it, suppose there's a function f which belongs to both m and n. So so it belongs to both m and n, so it belongs to their intersection, right? What that means is f is equal to alpha 1 f1 plus why do I call it alpha 1? No, it's alpha f1 plus beta f2. Okay? Or in other words, ft is equal to alpha times f1, which we define to be t, plus beta times f2t, which we define to be t to the fourth. But at the same time, because f belongs to n, we must also have that the integral from 0 to 1 of t times f of t must be equal, dt must be equal to 0. Let's see if that is true. So this is equal to the integral from 0 to 1 of alpha t squared plus beta t to the 5th dt. And this is equal to alpha t cubed over 3 plus beta t sixth to this divided by 6. And this is from 0 to 1. Clearly, this is not equal to 0 for every alpha and beta, because this is equal to alpha thirds plus beta sixths, okay, which this is not equal to 0 all the time. It is only equal to 0 for specific values of alpha and beta. And there you go. That's it. That means that the only way you can have a function f belonging to both m and n is if alpha and beta is equal to 0, or if alpha is equal to negative 2 beta. And you might think, oh great, then we can just plug in here negative 2 beta and we have a function f which is not equal to the 0 function. That's not true. Why? Because remember, there's a second condition for a function to belong to n, and that is that the integral from 0 to 1 of t to the 4th f of t is equal to 0. Let's see if this is true. Okay, so this is equal to 0, 1, t to the 4th times alpha, which we defined to be negative 2 beta, right? So negative 2 beta t plus beta t to the 4th dt. Okay, this is equal to 0, 1, negative 2b t to the 5th plus b t to the 8th dt. Okay, and this is equal to this is equal to negative beta over 3 t to the 6th plus beta t to the 9th over 9, okay, from 0 to 1, and clearly this is negative beta thirds plus beta 9th, and this is equal to 0 only if beta is equal to 0. But if beta is equal to 0, so is alpha, and there you go, that's the proof. Alpha and beta must be equal to 0, right? And so the only function f belonging to the intersection m/n is the 0 function. And so our second point has also been proven. So m intersection n is equal to the 0 function. Finally, let's do maybe the harder part of the proof, and that is that m plus n is equal to c. This is pretty difficult because we have to show that every function f that is continuous and real valued can be written as the sum of a function belonging to m and a function belonging to n. Okay, so how do we do this? Consider an arbitrary function h which belongs to c. And we want to write h is equal to f plus g, where f belongs to m and g belongs to c. Okay, sorry, not c, n. How can we do this? Well, we can say that the integral from 0 to 1 of t h t dt is equal to the integral from 0 to 1 of t f t plus t gt dt, right? But this integral here, t gt, must be equal to 0 because g belongs to n. So this is equal to 0, 1 t of ft dt. Okay, that's good, because we know what ft is, right? Ft is simply just alpha t plus beta t to the fourth. And so this is equal to, we calculated it earlier, this is equal to alpha thirds plus beta 6. So the integral from 0 to 1 of ht dt must be equal to this value right here. Okay, let's do the same with t to the fourth ht, right? This again is equal to integral from 0 to 1 t to the fourth f of t plus t to the fourth g of t dt, but again this is 0 because g belongs to n, and so this is equal to 0 to 1 t to the fourth f of t, and you can calculate this, it's equal to alpha 6 plus beta 9ths. Great. Now we have two variables here, alpha and beta, and we also have two equations, right? So we can always find alpha and beta in this case, right? Because for any function h, these two equations will always be satisfied because we have two variables and two equations. So we can always find alpha and beta such that if we write f of t, so we can always find alpha and beta such that if you write f of t equals alpha t plus beta t, then gt will be equal to ht minus ft will belong to n. And that finishes our proof, right? Because we've essentially shown with this that ht is equal to gt plus ft, which is what we wanted to show. Okay, so let's see how we can put this into practice, right? Say ht is equal to t squared. Then we want to find alpha and beta, right? If we find alpha and beta, we find f. If we find f, we find g, and we're done. So the integral t ht dt, right, is equal to, from 0 to 1, is equal to the integral from 0 to 1 of t cubed dt, right? And that is 1/4. But remember, we calculated this must be equal to alpha thirds plus beta sixths. So here we write this is equal to alpha thirds plus beta sixths. Now we do the same with t to the fourth. This is equal to t to the sixth dt, so 1/7. And this has to be equal to alpha over 6 plus beta over 9. So we have a system of equations, two variables, two equations, so we can always find alpha and beta. You can calculate them using just Wolfram alpha or by hand, and you will find that alpha is equal to 3/7 and beta is equal to 9/14. So we can write f of t to be 3/7 t plus 9/14 t to the fourth. And gt will obviously be ht minus ft, so t squared minus 9 to the 14th t fourth minus 3/7 t. And these two are the functions. Their sum is obviously t squared. This belongs to m because it's a sum of real number times t plus real numbers times t to the fourth. And gt also belongs to n, because if we take the integral of this, right, if you take integral of t gt from 0 to 1, you'll find that it is 0, and you'll also find that the integral from 0 to 1 of t to the fourth gt is equal to 0, right? And we know it's equal to 0, we don't even have to calculate it, because we forced it to be 0 right here by saying that it belongs to n. This here cancels out. So there you go. That is how you prove that indeed m direct sum n is equal to c, because m plus n is equal to 0 is equal to c. Their intersection is equal to the zero function, and they're both subspaces of c. And so the proof is finished.